Okay. Sorry for taking a bit of time, technical problems. So thanks for coming. I know it's Golden Week, so I was expecting there might be a few less of you. But yeah, there's many of you, it's very nice. So today's lecture will be about classification. Let's go back to, for a few seconds, to what we did last week. So remember that in the first lecture we introduced least squares regression. And then, least squares regression is a nice tool, but if I just tell you that you should minimize the residual sum of squares, it sounds a bit arbitrary. So we went through a few ideas which might give you some intuitions about what we are doing when we are doing least squares. The first one is probably the most important, is that it's the statistical viewpoint. So doing least squares regression is the same thing as assuming that to start with the function was linear and that you observe the observations are corrupted by some noise or are just a bit random. And that randomness is controlled by something called a residue, and the residue is distributed as a normal density. So in that case, doing maximum likelihood estimation is the same thing as doing just simple least squares. So the other important aspect of least square regressions that we've been through is the fact that, well, doing least squares regression is as if you were projecting. So you remember, I think, by now you probably remember this. We have a data matrix. The first row is just a constant, and then we have our observations, x1, x2, etc., x big N. And then we have real values, y1, y big N. Okay? So a lot of what we did was presented in this way. But if you flip things a bit, when we're doing regression, if you take the transpose of this, you can see variables as column vectors. So we have here a vector which is just once. And then we have all the observations like this. But what really matters is that we're looking at not observations. We are considering the values of the variables across all samples. So that we call this x1. So the first column is the column of ones, and then x2, etc., until we get xd, because we have d variables. And then what we try to reconstruct is this vector y, which has n observations. So we have d plus 1 columns and these d plus 1 column vectors and one vector. And we try to reconstruct this vector using this one. So of course, if you have a family of vectors and you want to reconstruct one vector with that family of vectors, then it's very simple linear algebra. And so we've discussed a few cases. What happens when those vectors span Rn? What happens when they don't? When they don't, we do a projection, etc. So in the typical case of regression, when you have more observations than variables, you have to project the vector of observed predicted variables, this y, onto the span of the vectors of the observed predictor variables plus the constant vector. So I think we've been through a few issues we discussed a few issues that may arise in the regression. I think probably one which is very important is that no matter what variable you add, even if it's complete noise, even if it's completely unrelated to this variable y, then you will improve the least squares criterion. Basically, geometrically, from the geometric point of view, it's easy to understand this. We have to project y onto the linear span of those vectors. If you start adding column vectors, even if they're noise, you're increasing the linear span. And so you're decreasing the distance from y to that linear span. So if the only thing that matters is reducing this distance, basically the sum of residues, then you might just as well start adding more and more variables. And even if they're completely noisy, that would be useful. But that doesn't translate into anything useful from our perspective. It's not very useful to add noise to a task. And I mean, for sure, it will not be useful if you have to reuse those values in the next observation. So we contrasted this with another point of view, which is that if you have too many variables, actually it's difficult to explain a phenomenon. And Occam's razor was the idea that the least variables you have, usually the best. I mean, if you can explain things with very little variables, it's always better than if you explain them with a lot of variables. So by taking into account this and other numerical issues, we've introduced regression, subset selection with the forward-backward idea. And then very, very quickly, I mentioned the lasso. So we'll talk a bit more about this in a few lectures when we talk a bit more about sparsity and kernel methods. But for now, today we will talk about classification. So if you have understood well regression so far, then classification should be quite easy as well, because it's fundamentally the same ideas. But there are a few differences which we will mention. So we will talk about classification in general. We will spend more time on binary classification. I will explain this. And then we will talk about some algorithms which are somehow the natural counterpart of the least squares regression. And those include logistic regression. Actually, I should update this slide because actually we will have time to talk about linear discriminant analysis. I will mention it. The perceptron rule, and a bit of support vector machine, but very briefly. And then from the next lecture, we will talk about statistical learning theory. So I will explain what this is. So let's start with classification. So the setting is exactly the same when it comes to just observations. We will assume that we have vectors of real values, and each data point is just represent a set of features. You remember that when we started regression, we were saying that there were observations, and then there was a variable that was interesting, that was important, that was maybe hard to measure or costly to measure, which we wanted to predict. In regression, that variable is a real number, or it might be a few real numbers. Now, classification is concerned with the case where YG is not a number anymore, but it's an element taken from a set, which is finite. And when the set is finite and has many elements, it's called a multi-class classification task. If S only has 2 elements, we call this a binary classification. So let me just give you a very simple example. Imagine someone, well, it's not really a very fun thing to do, but if you see an image of a fruit, what fruit is this? So usually there's just there's a finite number of fruit classes in the world. And so classifying a fruit out of those defined classes is a multi-class classification task. So actually I think this image was taken from a student project who were exactly trying to do that. Given the cut of an image like this, how can we predict which fruit it is? I'm not sure this is really useful, but there are very, very useful things in classification which concerns you more on a daily basis. The reason why we all have to write postal codes in addresses is because we have very efficient recognition algorithms to recognize from an image. So I will give examples later. So from an image of a number, of a digit, what number it corresponds to. And this really makes life much easier for the post. Actually, the post office doesn't even read, I think, the address. You could, in most cases, I mean, this happened to me at least a few times. I mistook some addresses in my Amazon order, but I put the post address of another location, and it was sent directly there. So I put the postal address of my home, and then I put my full name and then address here in Kyoto University, but everything was sent directly to my home. So that's the only information that the post office needs to distribute your mail. And this is a canonical classification problem. So after that, there's lots of applications, of course. I was talking about Amazon. You know that Amazon usually has an organigram of products. So if there's a new product that comes, they have to classify it somewhere in an existing class. It's actually a big problem for them because they probably have millions of products now. So they cannot afford having someone do this for each product. So they have to classify this automatically. This also applies to music, of course, movies, etc., etc. In bioinformatics, it's also a very important problem. There's a few tens of thousands, I think, of proteins. We know the functions of some of them, very, very few of them. Can we classify a new protein into one of those functional classes? Can we predict what it is used for, etc.? So binary classification is a simplified version of multi-class classification, but it's a fundamental one in the sense that actually many multi-class classification algorithms end up being an improved version, if you want, of binary classification, adapted version of binary classification. So there's lots of, if you look a bit into those variations, you will see names such as one versus rest classification, one versus one, etc., etc. So many multi-class classification algorithms reduce at some point to a binary classification. So binary classification is important to study. So it's also useful in practical life. So for instance, using elementary measurements, guess if someone has or doesn't have a disease. So sometimes a disease is difficult to detect at an early stage, so it might be just a predictive task. Or sometimes it's also very difficult to measure. So for instance, if you have a fetus in the womb of a pregnant woman, it's usually very dangerous to try to pick any sample from the fetus. You might cause a miscarriage. So in that case, we really don't have access to the information, but we want to predict whether the baby is at risk for some disease. And so in that case, you use classification. So using a lot of information, you can try to guess if that baby has or doesn't have problems. And that's used daily to screen fetuses in an early stage for any kind of a disease. So pharmaceutical companies might be interested in this is called virtual screening. When they have candidates of molecules for medicines, they want to know very quickly which ones might be toxic or not. So that's a binary classification task. In an airport, if you want to be able to screen passengers efficiently, then you might want to have an automated system that can directly classify passengers as maybe suspect or not suspect to speed up checking procedures, etc., etc. So you might wonder why we need to use a new name for binary classification since we have already developed some tools for linear regression, for regression. After all, classification is just building again a function that goes from RD, your space of observations, to the space S of labels. In what sense is it very different from what we've seen so far? Well, it's different because exactly as in the previous case, in the linear regression case, we need to evaluate the accuracy of a function f to select one. This is the way we do things in machine learning. We have a training set, and we try to see if our current function f kind of agrees with the data. And agree with the data is related to seeing whether your f agrees with f of xj is not too far from yj. But what happens if you have a linear regression or a real valued regression task? Well, it's very easy to measure that similarity. Well, it's not very, but at least we have mathematicals to do that. And you haven't doubted my formulation when I introduced the least squares regression, because somehow it makes sense. If you want to predict rents, for instance, if I predict, for instance, 37,354 yen for a rent of an apartment, and actually the real rent was 36,000 yen, well, you can quantify this difference as being 1,354, and it's not too bad. If my prediction had been 36,200 yen, it would have been an excellent prediction, right? So that quantity, the difference, the absolute value, whether you square it or not, is probably a good a good measure of how wrong or right my prediction is. And this is given to us because R is a metric space. There's a closeness between possible answers. You can say this is close to this, whereas this is far from this. And it's also an order set, so it's very easy to give this order and see whether we are on the left or on the right of that answer, etc., etc. So there is some kind of hierarchy. What happens when we have discrete labels? Well, this is the real problem. I think maybe the bottleneck of classification compared to regression. The reason why classification deserves more study. Well, it's because usually there is no distance or order that's available in a set of labels. There's no, if you have to classify pictures as being pictures of dogs or cats or mice, there's no order, there's no clear distance between this. If you have to classify musical tunes into genres, it's difficult to say that jazz is superior or less than bossa nova, and that kiwi is further away from banana than it is from an apple, or etc., etc. So this creates challenges to quantify how well we are close to yj or not, if we predict f of xj. So let's give you an example. So this is really one of the canonical multi-class classification problems. Those labels here are taken from a database which is called the MNIST database, MNIST. So it's a very famous database. It has been around for at least maybe almost 20 years maybe now. And it's a database of tens of thousands of handwritten digits. Okay. So when you look at those, they're all fairly easy to guess for us. This is really trivial almost. We all know that this is a 2, this is a 7, this is a 1. So there might be some variations depending on the country. Maybe 7 you want to add something, or in Europe you might add a bar, etc. But more or less we know what those numbers are. Of course, for a computer it's a bit more challenging because it doesn't have any clue if you just do not provide the algorithm with some information. So the MNIST database tries to do that. It tries to test classification algorithms by providing 50,000 training images and 10,000 test images. So suppose we know the information for those, I think there's like 2, 4, 6, 8, 10, 20 digits, and we know the actual values of each of those digits. And we want to build an automated recognition system. So what would be a recognition system? It would be something that would take as an input a vector of maybe this is 20 pixels times 20 pixels, and each pixel is a gray level. So that makes a vector of R400. So each image X belongs to R400. Well, actually, it's probably closer to 0, 1 to the power 400 than R400. And using that data, so many vectors of R400, we want to learn a system, a multi-class classification system. So of course, if you see this image and your prediction is 5, it's not necessarily better than if you had predicted 0, right? Although 5 and 6 are closer numerically, predicting 5 for this is not better than 0. So this is an example where it doesn't work. So what people do usually in classification is the first step is just using something called a 0-1 loss. This is what we will use in this lecture. So what is the 0-1 loss? Well, 0-1 loss is just the idea that if all mistakes are equally wrong, that is, if the image is a 6, but any other digit to me sounds equally wrong, it's the same mistake to say that it's a 5, a 4, a 3, or a 10, or a 0 or a 9. Then you can consider the 0-1 loss. And what is the 0-1 loss? It's very easy. It's just to say that the loss of f of xj when you predict f of xj given yj is going to be 0 if you're right and 1 if you're wrong. Okay? So it sounds naive, but this is how most classification algorithms are built. And what you should probably see also is that this introduces some problem here. It's not exactly, this is a discontinuous function, right? Okay. So depending on whether you change a bit xj's value or whether you change a bit f's parameters, then you will have a jump. Maybe the loss will be 0 or will be 1. It cannot be in between. Whereas with RANDs, with the real valued regression, then the mistake is smooth, basically. If you predict 36,200, it's very close to, the error would be very close to 36,201. So that's just a consideration. What you have to do is, however, be careful. Sometimes some classification problems can be handled fairly well using regression. So here's an example, for instance. So this was part of the idea of the Netflix challenge. Imagine that you have the problem that you want to predict whether a user will like a movie or not. And the prediction that you want to make is whether the user will grade that movie on a scale from 1 to 5. So there are only 5 possible answers, 1, 2, 3, 4, 5, because the user can only write those answers. And you want to predict the rating. Well, it seems to be a classification problem because there's only 5 possible outputs. But in most cases, people would agree that this can be handled with regression. Why is that so? Well, because you just, in that case, predicting 3 when the answer was 5 is worse than predicting 4 when the answer was 5. So it really depends on the modeling and the assumptions that you make on the data. So in this case, it would make sense. So let's let's describe a bit what binary classification is. So binary means that the set of labels is just of size 2. So in the literature, people would say that maybe S is 0 or 1, or minus 1, 1, or minus and plus, or yes and no. This is all equivalent. It's just all the same thing. So sometimes, mathematically, it's useful to use minus 1, 1 for some reasons. So again, the data is the same. We have vectors. And if we need to learn a function f which will give us a yes or no answer or minus 1, 1, then we need some training data. And training data comes as the vector and the correct answer for that particular vector. Okay? So this would be our training set. It's the same thing as before, except that yi is in 0, 1 now, not in R. So just like in the case for images here, your input vectors are usually quite large. Maybe 400 here. This is a very simple task, but the size is already 400. It's very typical that in binary classifications, the dimension D here can be, I don't know, 40,000, 50,000, 100,000. Sometimes if you have applications in natural language processing or image processing, you can have a few thousands of features, and then in some more extreme cases, you can even have millions of features. So sometimes in processing of information on the internet, there are so many features that you can get to the million. But just for illustration purposes, from now on, I will display a few images in dimension 2. So the reason is just that that's the only way you can have an intuition. It's easier. But the ideas will be the same for higher dimensions. So imagine that I have my data set here. My data set is just a bunch of points, which I have colored in blue and red. So this is, again, minus 1, 1, yes, no, minus, plus, etc. So what would be a classification rule? What is it that we're trying to learn? What we're trying to learn is basically a partition of the whole set of RD, or maybe in that case 0, 1 to the power 400, into 2 sets, an area which would be blue and an area which would be red. And these 2 sets have absolutely no reason to be convex or connex or anything. They can be just actually the union of 2 smaller sets. So for some reason, maybe this might be a valid classification rule. So whenever one new point arrives, it has to fall into one of those 2 sets. And this is how you define the label. So from a computational point of view, it's very difficult to describe sets exactly like this. So what we do is that we define those sets as the level sets of a function. So what do I call a level set? Well, I will say that actually those areas, blues and reds, are just the result of using a function f and selecting all the points x such that f of x is positive. So that might be, for instance, the red area. And all the points x such that f of x is negative. And that might be the blue area. Okay, so if the function is regular enough and it's defined everywhere, then using those two subsets that I call the level sets, then I get a partition of my space, and that's enough. I don't need to describe exactly the shape of the areas where there's a blue and there's a red. That would take a lot of time. I just focus on the function, and then from that function I learn my partition. So, of course, it would be very difficult to try to consider very, very weird functions. Well, it's not necessarily difficult, but just as with the linear regression case, usually what we try to do is at least consider functions that are regular enough, and what can be more regular than a linear function. So this is what people call linear classification. A linear classifier is a prediction tool, a function, that will basically split the space into two half spaces, so the blue and the red area. And it will be parameterized by a hyperplane normal, the normal vector, and a constant. So straight lines, hyperplanes, we call them hyperplanes when the dimension is higher, are the simplest type of classifiers. So what do I mean by a hyperplane? Well, a hyperplane is a set in RD defined by a normal vector. So maybe I don't need to make a drawing, but it's just two elements, a normal vector C and a constant B. And these two vectors, so the vector has to be non-zero. And this set is just a set of X in RD such that C transpose X equals B. Okay. So intuitively, what you should think is that the C direction gives you the orientation of the hyperplane, and the B constant gives you basically the location of that hyperplane. Okay. So if, for instance, you consider the hyperplane HC0, then it's the set of points X such that C transpose X equals 0, and that includes that would include 0. Make sure. So that's C. And of course 0 is such that 0 transpose C equals 0. So 0 belongs to the set of points X such that X transpose C is equal to 0. Okay? Actually, this is called the orthogonal of C. But then if you want to slide a bit that hyperplane, you might want that C transpose X is equal to B. So of course, if you start sliding, then you have something called an affine space. So this is called a vector space, because if I just add vectors taken here, they would all be such that C transpose X is equal to 0. If I take X1 and X2, this is just a side note. If X1 and X2 belong to HC0, then X1 plus X2, of course, belong to HC0. Okay. So this is just one observation. So you can easily prove that this is a vector space, but this is called an affine space. So affine. When B is not 0, this is called an affine space. Because if I take 2 points here, they're not necessarily The sum will not be in that space itself. So once I have defined this hyperplane, basically I can very easily define two sets, two half spaces, which are the set of point x such that C transpose x is smaller than B, and C transpose x is bigger than B. And that, of course, when you unite both, you just recover the whole of RD. So this is just how linear classifiers work. It's just a direction, a constant to place the hyperspace, and then just split the space into two halves. So now that we've just defined our model, if you want, of at least the classifier model that we're looking for, the big problem now is, given data or a training sample, how can we choose the best possible C star, B star? That's the problem of linear classification. So again, this specific question, given a training set, so points in RD, and then labels, 0, 1, or minus 1, 1, etc., how can I find the best? And I'm not even really sure what best means. C and star and B star to define this cut of the space into. Okay. So this question, you can give it many different answers, and to each answer usually there's an algorithm. So to each different intuition about what you want to do, there will be a different algorithm. So I will present 4 of them. I think it should be fine. And we'll go through some of them. The support vector machine, probably, I will just give some concepts, some ideas. But those 3, you should have a more or less clear idea of how they work by the end of this lecture. So let me just start with the problem. Why is it a problem, actually, to define a good C star and B star? What is exactly at stake? Well, suppose we have 2 sets of points here, which are very well separated. We have blues here and reds here. Of course, it is sometimes, and in this case it is the case, it is sometimes possible to separate them perfectly. So you might wonder what is exactly at stake. It seems very easy in this case. But when you choose one line, for instance, you might choose this line or this line or this line. They might look all equivalently good on the training set. But the problem is what happens when you have more points that appear after that. After that you have learned C and B. After that you have chosen that line. Of course, if I have a point here that appears in this area, and my choice for the classifier was this line, then this will be classified as a red. I would say that this is a red. If I had a different idea of what was a good hyperplane, I might have selected this line, and this would have had consequences, because this very same point would have been classified as a blue this time. So you can see that what's at stake is not so much whether we are able to separate well blues and reds in a training set. What's at stake is what will happen when we will see more points after that, and will we make a lot of errors? Is it likely that our classifier will be useful? So it's a bit somehow the same idea as linear regression, the same problem that we've raised with the linear regression. If the only objective is to predict very well, that is, reduce as much as possible the residual sums of squares on your training set, then you can just add noise variables and you will improve the performance, and then everything will be fine. But then what happens next is the problem, right? When you have a new point, it intuitively doesn't make any sense to predict it with noise. So this is the same idea. If you're just looking at the blue points and red points that someone gave to you, then it's very difficult to make a very nice, a good choice between this one. There's no reason why you should prefer this one or this one. However, when we add some of the ideas now, you will see that there are some ways to do that. So the first thing, probably one of the most simple classifiers, is called the linear discriminant analysis, or Fisher's linear discriminant analysis. So much like we started with the Gaussian residues to give an intuition of least squares, LDA works with the Gaussian density to provide another interpretation. So I assume you all know what the Gaussian density for real numbers is, right? It's a density probability for real numbers. Here it's centered at 0 with the variance sigma. Basically just says that if I have a real number that appears, its probability, its density is proportional to exponential minus 1/2 of x squared. So if x is big, this is very big, this is very, very small, and so the probability is very small. That's why you have the bell-shaped curve. I think that many of you should know what is the multivariate generalization of the Gaussian density, but if you don't, I will just describe it very briefly. So the Gaussian density just gives you an idea of the randomness of real numbers, okay, non-negative. Just real values. What if we want to measure randomness in vectors? That is, we're not just interested in see how likely it is that a number appears, but we're just interested in seeing how likely it is that a particular vector appears. What would be the translation of that with the Gaussian model? So this is what people call the multivariate Gaussian density. And it's built in this way. If a vector, random vector x, is distributed as a Gaussian density, multivariate Gaussian density, with a mean vector mu, which is in RD, and a matrix sigma. I'm sorry, I should have written this explicitly. So mu is in RD, and sigma is in RD times D. And sigma is positive semi-definite. So if you started doing the assignment, you know what this is, what this means. Then we say that the density of x, of a particular vector x, is this number. This is a normalization factor. It's just a number that depends on the determinant of this positive definite matrix. And then there's a number that comes out. I'm sorry, I forgot to put a minus here. That's a big mistake. Exponential minus x minus mu transpose inverse of sigma x minus mu. So the way you compute the density of a vector is easy. You just you have a vector x, you subtract mu. Okay, I will put here, this is a parameter. So mu is the mean parameter. And then you take the transpose of this, so we have a flat vector. Then you multiply it by sigma minus 1. So this is the inverse. So actually, it's positive definite matrix. Is that right? Yeah, positive definite. And then you again multiply by x minus mu. Okay, so this is a number, of course, because we have a row vector times a matrix times a column vector. And then you take the exponential minus that value, and then this will just give you a number. So with the Gaussian multivariate density, we have arguably the most simple probabilistic probability on vectors. And so this is a bit what a random draw of points would look like in 3 dimensions. So here we have vectors of R3, D equals 3. The mean is this red point. I have represented the positive definite matrix sigma as an ellipsoid, because you can actually represent such matrices as ellipsoids. It gives you basically the directions, tells you a bit the directions of where those vectors will be concentrated. And then you have samples from that distribution. So if you're not very familiar with this distribution, I encourage you to double check it. So why is it useful in the context of classification? Well, because linear discriminant analysis uses the Gaussian multivariate density to form an answer. What LDA assumes is that the points, here I just put them as 0 and 1, two classes, are generated by two different Gaussian densities, two different Gaussian multivariate densities. And so how does LDA proceed? Well, it says, okay, I have red points, I have blue points. I assume that they were drawn from a Gaussian multivariate density. What I will try to do is compute for each red and blue the maximum likelihood estimators of the mean and the covariance of the mu of this parameter mu and this parameter sigma. So again, I don't have access to the real parameters, but I can compute the estimators. So if you remember with the Gaussian density, it's very easy to compute those estimators. It's just the mean of the values and the standard deviation of the values. Where in the multivariate setting, it's very similar. To compute the mean and the covariance of mu 0 and sigma 0, you just take the mean of the vectors and then take this mean of that tensor product, xi minus mu 0, xi minus mu 0. And then you do the same thing here with the other class. So you're left with two different means and two different covariance matrices. And now, with those two means and two covariance matrices, you have two densities. One is called P0 and one is called P1. Okay? Here I've just represented them as I equals 0 or 1. You have Pi equals this. This is, again, I'm sorry, I made the typo. I copy-pasted this. There's a minus here. Again, there's a minus. So you have the first probability, 0, and the second probability for 1s. And what you do is very easy now. You just say that a new point that you haven't observed before belongs to class 1 if the probability for 1 is higher than the probability for 0. Okay? This is called a generative approach. You assume that your points have been generated by a model. In that case, it's a multivariate Gaussian. And then you just say, if there's a new point that arrives here, let's put it here, I will compute the probability that has been generated by this multivariate Gaussian, by this multivariate Gaussian, and the biggest wins. The one that gives me the highest probability wins, and I just decide this. So if you just go through some computations, so for instance, you might take the logarithm. This is equivalent to saying that the logarithm of P1 is bigger than the logarithm of P0, etc. Then this is actually the formula that you get. You will say that X belongs to class 1 if you have this quantity here, bigger than T. Again, those bars here stand for the determinant of the covariance matrix. So you have the determinant of the covariance matrices which appear, you have those products, etc. And then you will say that it's 0 if this is smaller than T. So T, sorry, I didn't write it. T is some constant which appears by stacking a lot of a few computations. So this looks quite easy, but still it's not a linear function, right? If you look at this, this is a quadratic function of x. Okay? So this is not a linear classifier yet. So it becomes a linear classifier when you assume that the covariance matrices are the same. So in that case, you would have to go again and estimate again the covariance matrix. But then if sigma 0 and sigma 1 can be identified, it's easy to see that this reduces to a simple dot product. And the value of omega here is just the inverse of that covariance matrix times mu1 minus mu0. So the vector, the normal vector c or omega here becomes this, and then you have a linear boundary. So what happens in practice is that if you assume that those two ellipsoids have the same shape, what becomes really important actually is the distance at which your new point is from each of those means. But it's not exactly the Euclidean distance, it's a slightly different distance. It's called the Mahalanobis distance. But again, this is just the basic intuition behind linear discriminant analysis. So there's another very, very popular tool. I think it's probably more popular than LDA, which is called logistic regression. So it sounds a bit contradictory because I've been telling you that classification is different from regression, and then here I have the regression which appears again. So let's provide an example to introduce this idea of logistic regression. I'd like to provide an example where I will show you that using regression for classification is not a good idea sometimes. So assume that I have taken points randomly between -10 and 50. Okay? Each xj is just a real value between -10 and 50. And then I have decided that a point would be 0, a label 0, if its value is smaller than pi. So pi is actually the real value pi, 3.14, blah, blah, blah. And it would be 1 if xj is bigger than pi. Okay? So this is a completely artificial task, which I'm using just for illustrations. So what happens if you fit, so this is the real classification if you want. As long as the point is below pi, it's 0. And when it becomes pi, above pi, it becomes 1. Okay? So let's show how this works. So this is also online, so you can check it out. So here is the way I've just generated my points. So I define the minimum is -10, the maximum is 50. I will consider 20 points. And then I just sample points between min x and max x. And then I just define my label. Okay, so I have x and y. Okay? So those are the points above, and those are the points below. So it's ones and zeros. So plot. So we're going to plot. So this is basically my classification function, if you want, that I would like to learn. Now, what happens if I run linear regression on this? So I'm going to plot again. So suppose I feed my linear regression tool with those points. A few here, a few here. Those are valued at 0 and those are valued at 1. Well, I'm sure you all know by now what we should do. We add a vector of 1s, and then we compute the vector alpha, and then we just plot everything. And this is what we get. This is our linear regression function. Okay? So obviously it's quite wrong, right? If you look at what it seems to predict, it's induced in error by the fact that since it relies on the least squares error, whenever it will predict this value and the actual value was this, it will say, okay, I'm making an error, which is this distance to the square. And it doesn't really make any sense, right? Especially in this area. So we see that if you just use regression as it is, well, there's very little that regression can make. And so what you could do, for instance, after you have run this regression to define your decision, is saying, okay, whenever I will predict that it's above 0.5, this might be a 1. Because in the end, what you want to predict is 1s and 0s. So if you predict 0.8, that's not a prediction that's valid. So you would predict maybe a 1s here and zeros here. And so you see that you're completely off, basically. Instead of setting a threshold at pi, you're setting a threshold somewhere at, I don't know, 15. So the question is there, however, a way we can save regression, that we can make it useful for the purpose for the purpose of classification? And there's one way, and it's called logistic regression. And why is it called logistic regression? Because logistic regression builds on regression and on a function called the logistic map. So this is the logistic map. This is called the logistic map. It's a function. It's 1 divided by exponential minus z plus 1. If you plot it between minus 4 and 4, this is the function that you get. So you can see it like a smooth. It looks a bit like an arc tangent. It's like this function. For any values, g will always be between 0 and 1. Okay. So again, 1 divided by exponential minus z plus 1. So what is the basic idea of linear regression? Well, if you just directly apply regression to a classification problem, you will work hard to find a C and a B. So I would call this alpha in the regression setting, that approximate 0 and 1. But we know this is pretty much impossible in many cases, because if you take the dot product of two vectors, there's no reason they should be bound between 0 and 1. Okay? So instead of doing that, instead of predicting, instead of really trying to fit as hard as possible the C and a B on your data, well, you will basically take the result of C transpose xj plus B, apply the logistic map to that result, and try to fit it then to 0 and 1. And why is it better? Because the logistic map is always between 0 and 1. So whatever the input of your regression here, whatever the value you're predicting here, g of that will always be between 0 and 1. So it will be somehow more natural. So your model, the logistic regression model, tries to find C and B such that 1 divided by exponential blah, blah, plus 1 is not too far from 0 and 1. And now it's not too far from 0 and 1 in a quadratic sense. So once you have found C and B for a new point, you will predict that this new point is a 1 if this function is bigger than 1/2 and smaller, and 0 if it's smaller. So let me just give you a probabilistic interpretation of logistic regression. So suppose there is a probability density P of xy on couples x, y. So the first half is your observation, the second half is the value you're trying to predict, the binary value. So we will use this setting a lot from next lecture. The fact that we assume that all the observations that were found in nature that someone gave to you arise from samples of a density. So suppose for a minute that we know this density. So ideally this is something that only God, maybe, if you believe, can know. Only we can never know this. Only someone that has a perfect knowledge of the universe can know exactly what is the probability of seeing, I don't know, a patient with such and such features, and whether that patient has or doesn't have the disease. If you look at the ratio here that I'm forming, here's the ratio which is the probability that y equals 1 conditionally to x equals x divided the probability of y equals 0 conditionally to x equals x. So if you're not familiar with the probabilistic language, this is just the following idea. I assume that features and labels are related in some way in nature, which is governed by this probability. And now there's something that I call the conditional probability, which is that, okay, you give me just the first half of the information, which are the features. What is the probability that that sample here has a label of 1? And what is the probability that it has a label of 0? Okay. Of course, if you take if you forget about this line, this plus this is equal to 1, always. Okay? If you just give me information about a patient, the probability that this patient is sick plus the probability that it's not sick is equal to 1, okay? If it's a binary variable. So the ratio here is called the odds ratio of a given point. So why is it an odds ratio? Well, because if this is bigger than this, if this is very small, this will be huge. This ratio here will be very big. And this quantifies how strongly we can make the prediction that actually this point here is more likely to be a 1 than a 0. So obviously, if this ratio here is bigger than 1, then it is more likely that y equals 1 than y equals 0 for that particular point. If that ratio is smaller than 1, then it's more likely that y equals 0 than y equals 1. In other words, if the logarithm of this ratio is positive, so it's the same thing. Here I'm saying the logarithm is, the ratio is bigger than 1, the ratio is smaller than 1. It's exactly the same thing as saying the logarithm of the ratio is positive or negative. Okay? So if I take the log ratio, this will give me an idea. Of course, this is all assuming that I have access to this very important information, the density. So what is exactly logistic regression doing? Well, it's assuming that the log odds ratio follows a linear relationship. This is what you will get if you work around a bit with the equations that I give you. What it's basically saying is that the log ratio here follows a linear relationship. So this can be very big. When this becomes huge, it's just saying that the log odds here is big, and it's just saying that this probability is bigger than this one. When this is very small, negative, very negative, and goes to minus infinity, this log odds becomes very negative, and so basically this ratio becomes very small. So the nice thing about logistic regression is that I just told you that I'm assuming that this is the model, but this is linear, right? So in the end, the only thing that matters is whether C transpose X plus B is bigger than 0 or smaller than 0. Okay. So again, we have a linear classifier. The output which is generated after that is different, but the linear decision, which will split whether someone is likely to be 1 or 0, is a linear function of the features. So here's an interesting point, which we might discuss again if you follow the pattern recognition course. Here I have assumed that the log odds ratio here follows this linear relationship, right? But if you look at, I have not assumed anything on the shape of P itself, on the probability P itself. So this is an important remark. In terms of modeling, I'm just modeling the ratio. I'm not giving an explicit model for P. Okay, so those are two different things. So again, so we're assuming that since the probability of y equals 0 is equal just to 1 minus the probability of y equals 1, I just substitute this in this part here. And then what I get is that what I'm doing is I'm assuming that the probability of y equals 1 given x is going to be this quantity here. So the way you can intuitively see this is that the predictor variables contribute linearly to the increase or decrease of the probability that y equals 1. So I'm sorry, it's not really exact. It's linearly in the sense that here, depending on the features, you will have a linear increase. And then using the logistic map, this increases or decreases the probability that y equals 1. So, okay, so now that I have defined this model, how can I actually estimate those C's and B's? Okay, so far I've relied mostly in the regression setting on least squares regression. Is this the same thing? Well, it's a bit different because we have this function g here that appears in the middle. So let me just give you an example. Imagine that you're flipping coins, and you're setting the probability that the coin is a head, or y equals 1 to p, and the tail is 0. Sorry, p y equals 0 is 1 minus p. Okay, so it's a binary random variable. What is the likelihood of a draw y, knowing that the probability of having p y equals 1 is p, and p y equals 0 is 1 minus p? Well, it's just this. It seems a bit complicated for such a simple thing, but if y equals 1, then the probability is p. This is equal to 1. And y equals 0, then this is 1, and then you have 1 minus p. Okay? So it's just a slightly complicated way of writing something very simple. Rewriting exactly this. Okay? This here and this are the same. So in the context of logistic regression, this probability of having a label y equals 1 or y equals 0 is going to depend on CB and xj. This is the model that we're going to assume. We're going to say that given observations, the likelihood that those observations have been generated according to this logistic regression is the product for each observation of the probability of having a 1 times the actual power, the actual observation, and probability of having a 0 times, to the power of 1 minus yj. So this is exactly what I was saying before. The features of xj contribute linearly to the increase of the probability. And then when you have an observation which also has a yj, you just look at them, and then you have the probability. And since all the observations have been independently sampled, we can get that the likelihood of this data set with respect to C and B is this function. So what we will do is use maximum likelihood estimation to estimate C and B. So you remember that when we were doing maximum likelihood estimation for regression, it was far more simple. The likelihood function, this was really the very first slide of the lecture. The likelihood function, so this is a bit like C, this is A, was this quadratic function. And it was a very simple quadratic, very simple to solve. If you remember the first lecture, we actually computed the gradient of this. And we showed that just using first order conditions, we could recover the solution, and there was the hat matrix, and et cetera, et cetera. The likelihood now that we get, now is this function. So it's a bit more complicated. We have again yj's, we have again xj's, and then we have again the parameters c and b's which appear. Thing is, how can we maximize this? Well, maximizing the log likelihood, if you do some basic math, you can show that maximizing the log of this is equivalent to maximizing this sum here. So again, it's not so easy as the least squares regression setting, but we get this expression here with the logs and exponentials. Unfortunately, there's no closed form solution for this. We need to run actually an optimization algorithm that will look for values C and B which maximize this. So you can prove that this is a concave function that has this bell shape in multivariate, in many dimensions. And so you can try to find the top if you want. And so there are many methods that work for this. So let me just show you how this would work. So you remember this ugly plot. This is really ugly somehow because we're trying to predict zeros and ones, and then we have this line which is returned by linear regression. So what I'm going to do, so this was just the logistic map. What I'm going to do is, okay, it's going to be a bit of magic because I'm just going to call a function called Logistic, which depending on the data and the y's, remember that here the data x is just the constant and the observation, and the y is just ones and zeros, will give me back the parameters of logistic regression. So let's look a bit at logistic regression, what it looks like. So this function Logistic. So I didn't program it. I got it on the web. So this is just a few starting points. But what you can see is that there is no hat matrix. There is no x prime inverse times xy. It's code basically. You have iterations, maximal iterations, and then you update, and then you compute gradients, etc., etc. And then so you loop basically over a few updates, and then you're really doing an optimization algorithm trying to maximize this objective. But if you look at the results, so let's compute. So t is two coefficients. It's just a constant, and because here remember we're in two dimensions only, so we only have one slope a or c, and then the constant. And then let's see what this looks like if you plot the result of logistic regression. So we have this is the original data points, and this is basically the result of logistic regression. So if you apply those weights here, minus 8 times x plus 28 plus 1, this is what the logistic map applied to C transpose x a curve looks like. So you see that it really matches, at least on the data set here, it matches much better the idea that we had that this is really the threshold that matters. Okay, and this is, it recovers basically the real classification problem. So I don't want you to think that logistic regression works perfectly just because it beats this. This was really terrible. This is much better, so it works well. It's not necessarily much better than, for instance, LDA. It's just another algorithm. What a nice feature of logistic regression, though, is that the output that it gives you, remember that what we're computing is this, right? So logistic regression doesn't only give you a number which you can threshold if it's below 0.5 or above 0.5. It's giving you something a lot more useful, which people really like, actually, which people especially, I mean, in applied, in biology or medicine, really, really like. It's giving you the probability. Sorry. Oh, I think running out of battery. It's giving you the probability that y equals 1. So that's much better, actually, than just telling you whether it's a 1 or a 0. Okay? So it's probabilistic inference. So usually people will be far happier if you tell them, for instance, and this is what happens in practice, if you have a fetus that might have a disease, you might say you're far happier when you hear your baby has the disease, or when it tells you your baby has a 53% probability of having a disease. Of course, it's much better to know that it's 53 because it's very borderline. Whereas if it's just 0 or 1, there's just a threshold, and if it's above 50%, then people will tell you that maybe the disease is there. If it's below, they will tell you no, it's not. So it's usually more useful to have this. And logistic regression provides you with a model to give you a probabilistic output. So people like it for that reason. So let me just now go very quickly through the perceptron rule. So this is a very important distinction that I would like to make. Both in linear regression, in LDA, or in logistic regression, we have used all of the data to form one criterion, so maybe the likelihood or the least squares criterion, etc. And we used all the data at the same time to find good parameters. There are other methods which are called iterative, which are different in nature because they don't look at the whole of the data, but they just look at one point in your data set after the other, in usually a random order. So this is the case of the perceptron rule. So this is why people call this an iterative algorithm. So again, here we will consider that S is minus 1, 1. It's easier to write equations. And what the perceptron rule does, it just starts from any arbitrary estimate. So again, if you think about logistic regression, least squares, etc., usually we didn't really have this way of thinking of starting with some guess and then improving that guess. Here in iterative methods, this is really important. We start with a guess, and then we will try to make it better. And by making it better, what we do is that we loop over the size of the data set until our estimate of the direction and the normal vector C and the constant B do not change anymore. So it's really a heuristic. And so what do we do is the following. We consider a point, a new point in the data set, xj. We add 1, which is the constant vector, and we consider its label. And then we look at our guess for that point, our current guess for that point. Do uj, which would be the guess. The guess is just the sign of omega transpose the vector and yj match. If they agree, then we're fine. If not, we change a bit the direction so that it will agree a bit better the next time. So there's not much else I can say except that it's maybe easier to watch it in practice. So let me just again show you some how the perceptron will work in 2 dimensions. So we have some blue points and you have some red points. We want to find a classifier. So we will start with any classifier, any line. So here I just chose randomly this line. So what you can see is that obviously this classifier here is pretty wrong. It's saying that this area is blue and this area is red. Okay? As per the way that I have parameterized it. So again, this is important. Unlike logistic regression, we're going to scan the database one by one. So it has a very nice advantage if your database is a few terabytes or petabytes. It's much easier to look at observations individually than taking the whole of the database that you cannot even load in your computer. So this is why it's popular in very large scale settings. So imagine that we've selected this point randomly. So obviously this point right now is not well classified. It's on the blue side of the hyperplane, and I've been told it's a red. So I need to do something. And what I will do is I will try to tilt a bit the hyperplane so that at least next time it will not be wrong. And so this will be the next, if you want, the next iteration, the value of my hyperplane. So now, at least for the previous point, I'm not wrong anymore. And for this one, I'm not wrong either. So I don't need to change anything. For this one, of course, I'm wrong here. So again, I'm going to tilt a bit the hyperspace by updating the direction. And this is what I will get, etc., etc. So what you can see is that this will work as long as you're selecting points nicely. If you look at this, there's only one point that might change, again, your guess, and it's if you select this one, right? So if you have a lot of points, of course, you might wait for a lot of time to select this one. OK, we were lucky we selected it. So now we just update, and then now you can loop for 100 times, and then if nothing has changed for 100 times, then you say that it's over. So it's quite different from the other methods that I have introduced. It's a lot more naive, but because it is naive, it works all right. So the last classifier that we like to talk about is the support vector machine. So I have a few minutes to introduce it. So again, let's go back to the fundamental problem, which was I have blue points, I have red points, I have to draw a line somewhere. How can I select that line? What is a good idea? So we've seen that LDA thinks that the blue points and the red points are generated with the Gaussian. So that gives us a hint of how to select that line. We've seen that logistic regression tries to come up with an interpretation, probabilistic interpretation, which will help us draw a line. Here is the interpretation behind the support vector machine. The support vector machine considers something called the margin. So it's fine to separate points, blues and reds, and split them with a line, But the SVM, so support vector machine SVM, says that what's more important is not so much being able to split. What's more important is being able to have a buffer around the separation surface. And the buffer is how long can you go, how far can you go on both sides until you touch one point. Okay? So obviously the buffer for this line is smaller than the buffer for this one. Okay? So if you think that it's good to have a big buffer, which line should you select? And this is exactly what the SVM tries to do. It will run an algorithm that will maximize the size of that buffer, and then we'll decide that this is the best possible separation hyperplane. So why does it have this weird name, like a support vector machine? It sounds a bit like a science fiction, I don't know, title or something. Well, the reason is that the points which are eventually touched by the hyperplane on both sides are called the support vectors. And this is what we call support vector machine. So far this is a pretty trivial example, this illustration. But we're going to assume in the next minutes that the data is actually linearly separable. Of course, you could have data that's not linearly separable. You can have we could have so we could have had this situation where we have a few red points here and some blue points nicely set in this area. But maybe there's one blue point that appears here. And in this case, there's no way you can actually find a line that will perfectly split your two sets of points, as red on one side and blue on the other side. But for the moment, just for the simplicity of explanation, let's assume that this is the case, that data is linearly separable. That is, there exists omega and b such that for all points, omega transpose xi plus b is positive if yi equals 1, and omega transpose xi plus b is negative if yi equals minus 1. So we are going to give a formula to compute what we call the margin as a function of a vector w. But what I would like to insist is that defining just a hyperplane in itself it's a bit an ill-posed problem. Why? Because if I take w and b and I just scale them by a positive number, tw, tb, I get exactly the same hyperplane. Okay, so we're going to try to lift this ambiguity and lift this multiplicative constant ambiguity here. So this is how you parameterize the support vector machine. You would say that for a given hyperplane w transpose x plus b equals 0, the tube here will be the width of that tube here will be such that here the hyperplane will be set to be w transpose x plus b equals minus 1, and this hyperplane will be set to be w transpose x plus b equals plus 1. And we will try to basically grow this tube until it touches points. If you assume, if you take those, if you assume those conventions, those are just really simply conventions to simplify a bit this idea of a tube. Just say that actually an hyperplane is defined as x, w transpose x plus b equals 0, w transpose x plus b equals 1, w transpose x plus b equals minus 1. The width of that tube is twice this distance here. And if you compute it, if you take a point x1 and x2 such that x2 minus x1 is collinear with w, and x1 is here and x2 is here, then it's very easy to see that if you subtract these two, W transpose x2 minus x1 is equal to 1. And since you have chosen x1 and x2 to be collinear with W here, then you just have the relationship that W transpose x2 minus x1 equals 1, and this is actually equal to the norm of x2 minus x1. And so you have that this tube here, twice the norm between x1 minus x2, is equal to 2 divided by the norm of W. Okay? Because here you have that the norm of W times the norm of x2 minus x1 is equal to 1. Okay? So if you define your hyperplane as this, and you define the tube as this and this, here explicitly as W transpose x plus b equals 1, W transpose x plus b equals minus 1, like this, well, you know that the width of that tube is exactly 2 divided by the norm of W. Okay? So when I say that I want to increase that tube, I'm explicitly saying that I want to make W as small as possible. Sorry, if I want to increase the tube, I want to make W as small as possible. But I cannot make, if this was really the case, I would just make sure that W is equal to 0, right? Or a very, very, very small value. This would be an infinite margin. But I cannot take any W. Remember that I need that this tube here agrees with my labels. I need that for all points such that y equals 1, W transpose xi plus b is bigger than 1. And I need that for all points such that y equals minus 1, W transpose xi plus b is smaller than minus 1. This was by definition this idea, my convention. Okay? All the minus points are on this side, and all the the plus points are on this side, meaning all the points on that side are such that this is insured and this is insured. So if you look at those two conditions, they can be summarized with this one. The label, minus 1, 1, times W transpose xi plus b is always bigger than 1. This ensures that I'm always outside of the tube for the good observations. So what is the problem that the SVM will try to do? Again, remember, we're trying to maximize the tube, which means minimize the norm of W. Well, minimizing the norm of W or minimizing the square of the norm of W is the same. So since it's a bit easier from an optimization perspective, we just add a square here. But it's actually the same thing. With or without is the same. So we want to have a small W. But remember that we want the tube and that line to agree with theta, such that all the blue points are here and all the red points are here. And not only that they are on the good side of the hyperplane, but they're actually on the good side of the tube. They're outside. And remember, this is exactly why I, W transpose xi plus b, is bigger than 1, or minus 1 is bigger than 0. So this program, find W, which is of small norm, but which agrees with all this, where I can find a b here that will help me ensure this, is called a quadratic program. But I will not go too much, I cannot discuss this now, we don't have the time. I will discuss it again at the end of the course. Let me just close the lecture with an intuition which I think is more important on what the SVM tries to do. So suppose that we have two sets of points that are linearly separable. I have blue points and I have red points. In geometrical terms, knowing that two sets of points are linearly separable is equivalent to saying that their convex hulls here do not intersect. Okay? It's easy to see that the convex hull of the set of blue points, so the convex hull, if you don't know, is the smallest convex set. A convex hull of a set of points is the smallest convex set that contains all those points. You can very easily imagine that you're basically pulling a rope around the set of points and you want to make this rope as short as possible. And so this is the set of the convex hull of the set of red points. Here in this case, of course, there is a big intersection, right? Okay. But it's very easy to prove that if two sets of points are linearly separable, then their convex hulls do not intersect. In that case, you can find the red point in the red set and the blue point in the blue set, which are the closest to each other. So this is a program. This is that would be a linear program. It would be probably a quadratic program. You're basically trying to find the set of the blue point and the red point, which are the closest to each other. This is well defined. Just give me. This is actually usually called the distance between two sets. It's the minimum of the distance between x and y, where x belongs to the first set and y belongs to the second set. Well, what the SVM does is just find those 2 points and then take the bisection of that segment here. So in higher dimensions, this is just a line, and this would be a hyperplane. And this is the answer that is provided by the SVM. And the support vectors, so this is a bit more geometric, but would be the extreme points of the facets on which these 2 points lie. So in this case, this point lies on the facet, and those are the extreme points of that facet, and this point is a facet. So that's the intuitive explanation for SVMs. So there's another explanation when the points are not linearly separable. I let you check the slides if you have some time, but we'll discuss a bit more about this in the last lecture. So I will see you next week. Please remember that there's a homework that is due next Tuesday at noon. It has been uploaded on the website. So Tam made me notice that maybe the link on the email that I gave on my page is wrong. So let me just, I will correct it. So I'll be waiting for that report. And since it's more of there's no programming involved in that report, please feel free to write it down. If you want to write down with handwriting is fine. In that case, you have to drop it in the course box that's downstairs in this building. So I can accept both written and email reports. Okay, so have a nice golden week, and I will meet you next week.